Welcome back to the Pathfinder's Codex. Today we're jumping right into the next 3 practice shaders in the Godot game engine. We're going to demonstrate each shader to check out its input parameters, then dig into the code and mechanics to see how they work. You'll see what each shader parameter does, and then how they come together to replace the original textures with the brand new looks. If you're following along with the series, this is episode 2, so if you've missed the first 3 shaders in episode 1, be sure to check it out. That video goes over some of the most basic 2D shader concepts that we'll be expanding on today and in the rest of the series. First up is a shader that introduces the time feature to animate our output results. The RadialRotate shader. In this one, we're going to modify the texture with a spinning pattern of colors that rotates over time. The shader only has one input, and it allows us to control the speed of the spinning effect. Setting the speed to 0 will stop the spin. Setting it higher will increase the speed, and setting it negative will actually reverse the direction. Let's figure out how it works. First, we'll look at this built-in time variable. This time variable is a special built-in value that tells the shader how much time has passed since the shader has first started running. And by combining it with our speed uniform, we can use this to animate parts of the shader logic at any speed we want. We'll store this adjusted time in the variable t so we can use it later. Before we apply our motion, let's look at another common concept found in these shaders: the scaling of the UV and fragment coordinate system. In the first episode, we learned how to center ourselves in the UV space by subtracting the UV position from vector 2 0.5, and we're going to do the same here. This lets us create our effect at the center of the image instead of at the top left. And you can see what happens if we were to temporarily remove that part of the code. So now that we're centered, we're also going to multiply that result by vector 2 2.0. This is how we'll scale and zoom the shader in and out. You can do some interesting things with this type of scaling, and we'll see more of it in future shaders, but for now we're just going to keep it simple. This scales the entire UV space by a factor of 2, which will make our output appear zoomed out and smaller than it's actually supposed to be. You can see the effect this has on the output. For example, if we were to remove the scaling completely, then our rotating effect will get larger. On the other hand, if we have the values by multiplying by vector 2 0.5, the effect would be even larger. Great! Now we have the adjusted position of our pixel, centered and scaled the way we want it. We'll use this position to find the distance from, and the angle compared to, the center of the image. In the last episode, we used the same functions, and you can refer back to that video if you need a refresher. Now comes the fun stuff. Let's create the color output for the current pixel. We'll do that by treating each color channel, the red, green, and blue, in slightly different ways and at different speeds. First, notice that we're including the speed factor here, the variable t, in each of the channels. Then, each channel also has its own multiplier, so in this case, the blue channel will be moving slowest with a multiplier of 15, and the green channel will be the fastest with a multiplier of 5. By passing our angle and our customizable speed factor into the sine and cosine wave functions, we'll get the channel values that are not only based on their locations, but also based on their time that the shader's been running. And because we're using the sine and cosine functions, we're also getting movement that's periodic and oscillating back and forth. While it's not critical for this shader, we'll also cut the colors in half by adding 1 and multiplying by 0.5. In fact, you can change any of these values to fit your needs to try different variations. For example, if you really want to make the green channel pop out, you could remove the halving value. Or if you wanted the blue channel to spin really fast, you could change the 15 down to a 1, or even make it negative to change the direction of that channel. You can even take this to the extreme and remove any of the channels with a value of 0, and it might give you a better sense of what's going on with the other channels. Feel free to explore and try different values here. Next is another optional line of code. By using our pixel's distance from the center point, we can get a soft fade out as the pixels get further away from that center. We'll use the smooth step function along with the distance value and multiply the results into our color. Like before, we can remove this line of code to see what the impact is. The last line of code is where we assign our dynamic color into the output color. This should be familiar as it's how we've assigned output colors in the first episode. The only difference here is we're going to make the alpha transparency from the input texture and use that in the output texture. Basically, if the original texture had transparency at any given pixel, that transparency will also be applied in our output image. One last comment here. We're doing a full overwrite of the output image by using the equals assignment operator. This means we completely lose the original image texture in our output. Recalling back to the first episode, if we want to add our new effect on top of the input image, we would use the plus equals assignment operator, like this. Our RadialRotate shader is looking pretty good, and we can now use the time feature in our shader to make some interesting time-based animations. Next, let's move on to a shader that skews and stretches our original image using the powerful Vertex function. The ShadowEffect shader. For this practice shader, we're switching things up by working with a pixel art mech sprite that has a bunch of transparent pixels. It only contains a single input uniform, a flag that lets us control whether the shadow should be flipped left or right. And since our mech suit is facing right by default, we'll use the look right option for this. In previous shaders, we've been using the built-in fragment function to change the color of pixels. Next, we'll introduce the Vertex shader function. We'll not only change the colors in the fragment stage, we'll also manipulate the geometry of the image first in the Vertex stage. In Godot, the Vertex stage runs once per quad corner, before any pixel shading, giving us full control over the image shape. We can stretch, squash, skew, and even flip our texture using this function. A vertex is a point. Shapes with 4 points are generally called quads and sometimes rectangles. And since our sprites and textures are always rectangles, there will always be 4 points that represent the corners of the image. The vertex function actually supports more than 4 vertices, and there can be as little as 1 vertex in some cases. But for most of the 2D shaders we're working on, there's always going to be 4 corners to work with. The function runs once for each of the 4 corners. Okay, let's jump into the vertex function. Here's how we use it in this shader. First, we flip our mech's horizontal alignment based on the look right uniform. The vertex variable here is a special built-in variable that serves 2 purposes. It holds the original x and y coordinates for the corner being worked on, and it's also how we'll change those coordinates. We can feed any vector we want into this vertex variable, and the image on the screen will be adjusted accordingly. Notice how multiplying vertex.x by either -1 or 1, using this little array lookup, instantly mirrors the image when we toggle the flag on and off. Mirroring, check. Next, we can squash the shape. We'll do this by pushing the bottom 2 points up to the x-axis. To figure out if a point is one of the bottom 2, we'll check if its y component is negative. If it is, we'll move its y component up to 0. We completely overwrite the point's coordinates into the vertex variable to save this change. After all vertices are processed, the shape changes from its original rectangle into a half rectangle, where the bottom edge has been squashed into the x-axis. Squashing, check. As the last step, let's skew the shape to give it some perspective. We'll do this by pushing the top 2 points outward, based on how far they are from the center. First, we'll check if the point belongs to the top half, by seeing if its uv.y value is greater than or equal to 0.5. If it is, we calculate how much to move it by using the absolute value of its x-coordinate. Points farther away from the center move more, while points near the center move less. We then add this horizontal shift to our working vertex coordinates to save the change. This applies the skew to our already squashed quad. After all vertices are processed, this stretches the top half of the rectangle outward, turning the shape into a trapezoid. Skewing, check. So as you can see in the preview, these combined operations reshape the quad into a skewed box, and the texture inside the box will be skewed to match our new corners. With the geometry now reshaped, we're all set to move into the fragment stage and fill it in with a silhouette. We'll replace the original texture entirely with a shadow color that respects the transparency of the original image. The color for the shadow will be constant, but you can see what happens if we were to use a plus equals assignment operator here, instead of the raw assignment operator. The shadow would then get the same colors as the original sprite. That's not the effect that we want, so we'll stick with the assignment operator. The only problem now is that we've completely lost the original mech suit image, because we've manipulated the vertex corners. Let's fix that. To add the original image back into the picture, we're going to cheat a little and add a second sprite node. This is the first shader where we're going to use a second sprite to get the full effect. We'll simply nest this new sprite inside the existing one, so it shows on top of our shadow. And we'll give this new sprite the same size and texture as the first. Only this time we won't give it our shader material. Awesome, we now have a shadow effect appearing underneath our original unskewed sprite. And we can view the shadow with or without the original texture by hiding the new sprite node. We'll use this same two-sprite technique in the next shader. So let's check out the last shader for today, where we're going to surround a rectangular texture with a moving border. The Animated Border Shader, version 1. In this shader, we're applying an animated outline effect that looks like a moving dashed border. It has a bunch of input settings to control the look and feel. We've got one for the direction of the animation, one for the frequency of the dashes, another for the speed of the dashes, the overall radius of a circle, the thickness of the line, and the color of the border. When we get to the code, we'll see how each of these come together to create the animated border effect. Like the last shader, this one relies on two different sprites, one nested within the other. The main difference this time is that the second sprite will use a z-index of -1. This makes the shader effect show on top of the image instead of behind it. We'll re-enable that second sprite at the end after we've walked through the shader code. Let's start by introducing a new uniform hint for us to use. By using the source color uniform hint, we can choose a color directly from the inspector's color picker, instead of having to set the individual values for the 4 channels every time. It's a nice quality of life feature for sure. Okay, let's jump into the fragment function and break it down on screen. First, we center our UV like we've done several times before. Next, we'll create a circle by measuring the distance to our center position. We'll use the step function to decide if a pixel is inside our desired radius. Let's remove all of the other logic out of this shader just for a second. Then it'll be easier to visualize what this circle is doing. Okay, now let's lower the radius down to 0.5, and even further down, or back up. I usually keep this at a max radius of 1, just to make sure that the pattern extends beyond all parts of the texture. I'll crank it back up in a second. The next part of the code applies animation to our circle. We've used the arctan function in earlier shaders to get the angle relative to the center position. We'll do that here just like before. Next, we'll create a wavy animated effect that moves around the circle. We'll use our recently discussed time variable and a few of our input parameters, and pass those into the sine function to create a sine wave pattern. It looks like this. We'll also make the arms in the circle more distinct by using the step function, which gives us this. Now we're getting somewhere. We'll store this rotating pattern in a new variable because we'll need it in a second. As we're doing that, we need to make sure it uses the same alpha transparency that was sent in for the border color. It might not seem important, but this is required if we want to create partially transparent borders. Okay, let's push the radius back up so our pattern covers the entire texture again. So far so good. Our animated border is going to hug the inside of the texture edges, so what we want to do is create a mask. The mask will check if a pixel is near the edge of a texture, specifically if it's within our desired line thickness uniform. To bring it all together, we combine the circle with the mask. We can multiply the rotating pattern we stored above with this border mask, acting as the new transparency channel. If the pixel is too close to the center, the mask should erase it out, keeping only the pixels that sit close enough to the border. So now we can finally re-enable that second sprite holding the original image, and make sure it shows up behind our new border effect. And mission accomplished. It looks great, and we have a ton of customization options with all these input parameters. So in today's video, we've seen a mix of really creative techniques and reinforced many of the basics. With RadialRotate, we saw how time and trigonometry functions can be used to apply animated and oscillating patterns to a texture. With ShadowEffect, we introduced the difference between vertex and fragment processing, and saw how skewing the geometry can be used to apply simple shadow effects, even working with transparent pixels. And in animated border, we've used much of what we've learned so far to create basic customizable borders for our rectangular sprites. By trying these shaders and playing with the parameters in code, you'll get a hands-on feel for how these techniques work together to create fun visuals. It's all about experimenting with the tools we have, seeing the effects in real time, and having fun while learning new ideas. If you've enjoyed these breakdowns and want to see more creative shader magic, be sure to subscribe to the channel and drop me a comment. In our next video, we're going to go even further into intermediate and advanced shader techniques, so stick around and keep on experimenting. Thanks for watching the Pathfinder's Codex, and never stop learning.